Welcome back to Real Time Digital Signal Processing course. Today we will discuss continue with our fast Fourier transform. So, in the last class we discussed about how to derive the equations from our DFT, and then we drew the butterfly structure and then said that how our computation can be improved using FFT. So, today we will see that what are the finite word length effects in FFT. So, what are the one is the first one is we can have we are going to have round off errors. So, which are produced when the product WKB, as we can see, is truncated or rounded to the system word length. We have been seeing that when it is getting multiplied by this, a butterfly structure will be going to be truncated or rounded. Next one is what we have is the addition. So, which is going to cause overflow. So, errors. So, which results when the output of a butterfly exceeds the permissible word length. As you can see, there is a addition. So, when it exceeds the limit, then we will have the overflow. The other one is RWK, that is coefficients quantization errors. This is the third one what we have it, which result from representing the Twiddle's factors using a limited number of bits. So, because we cannot represent WK itself for infinite number of bits are not available depending on number of bits. So, we have to truncate our Twiddle factors. So, that will be causing us coefficients quantization or sine and cos function what we are going to store them. So, we will see first round of errors. So, what is it? We have taken here x naught plus j y naught. Instead of representing it as a, we have taken split as x as input, and this is x1 plus j y1. So, this we have our Twiddle factor is cos plus j sine function. So, you are seeing the multiply sign, and this is going to be multiplied by minus 1, and our output is going to be x naught dash plus j y naught dash. So, what we are going to assuming that each butterfly generates identical but uncorrelated errors. The maximum noise power at each FFT output is approximately given as equivalent to or Wn, it is nothing but e power minus j 2 pi by n, nothing but cos 2 pi by n minus j sine 2 pi by n. So, we represent cos function as c and then our sine function as s, and we are taking the negative sign inside. So, it is going to be c plus j minus of s, and then we know that our a is cos into x1 minus of minus sine function into y1. Same way our b is going to be represented in this fashion, and then we know that x naught dash is equal to our real part x naught plus a, what we have it, a is given by this equation, and y naught dash is nothing but y naught plus b given by this equation, and x1 dash will be x naught minus a, and y1 dash is going to be y naught minus b. You can verify whether we have got these equations correctly or not. Then what happens? Our butterfly computation requires 4 real multiplication, what we have you can see the thing here what we need it. Okay. So, 1, 2, 3 and then 4 real multiplications and 6 real additions. So, how many of them you can count here? This is 1, 2, 3 and then 4. So, we have another 2 coming from your these two a and b. Here 4 plus 2 what we needed. So, 6 real additions, taking into account our subtraction is equivalent to addition. That has to be kept in your back of mind whenever we do this additions. And next what we say is then what happens to our round of noise power, that is we call it as variance at the output of each butterfly is going to be given by. So, we have derived our noise power as q squared by 12. So, because we have 4 real multiplications. So, it is going to be 4 into q squared by 12, which is nothing but 1 by 3, and then we are substituting q is equal to 2 to the power of minus b minus 1 in terms of how many bits. It becomes 1 by 3 into 2 to the power of minus 2 into b minus 1, and then our this is at each butterfly. So, then we have how many butterflies we are going to have. So, we approximate it as, although we have n minus 1 is the thing, number of stages what we are going to have it, we have rounded it off to n. So, the noise power for n stages is going to be sigma naught squared is nothing but n into sigma b squared. So, when we substitute our butterfly sigma b squared, which becomes n by 3 into 2 to the power of minus 2 minus b minus 1. So, we need total number of butterflies required to produce an output sample is, so we will be seeing n by 2 plus n by 4, so on 2 plus 1. So, when you take the series expansion, so you will be seeing that it is nothing but 2 to the power of m minus 1, 2 to the power of m minus 2 or so on plus 2 plus 1. So, when you substitute it, so which becomes equivalent to n minus 1 butterflies are required. So, which was approximated as n. So, now you will be seeing that how the error is going to have its impact. So, here you want to compute x of 0. So, how many butterflies we need it? We have to go back from here. Okay. So, I need one butterfly here, and the previous stage to compute this and this output, here one butterfly is required in the stage 2, and this is the other butterfly required to compute the output of W this thing we need W n 0 in this case. So, 3 butterflies, and in the previous case you will be seeing that we need all the 4 butterflies here. So, this is 4 plus 2 6 plus 1 7. So, it is nothing but n minus 1 butterflies contribute for one output. So, this is x 0. If you take x 4 also, what you will be needing the same thing. So, as an further example, if you take x of 2, okay, this is x 0 and this is going to be x 1, okay. This is going to be x 2 and this is x 6 will be the output. So, you will be seeing when you count how many butterflies are required, you will be needing n minus 1 butterflies to compute one output. So, that is the reason why what we call it as, that is when we increase n, that is doubling n, which is equivalent to adding a stage to FFT. So, that is what is going to happen, doubles denoise power. To retain the same noise power, we increase the word length by 1 bit. So, we will be seeing that sigma naught squared is nothing but we are doubling the n 2 into n divided by 3 into 2 power 2b and then increasing 1 bit. So, it becomes 2b minus 1 plus 1, which is going to be 2 power 2b. Then what happens? The real and imaginary parts of our input sequence are uncorrelated, and that each has an amplitude density that is uniform between minus 1 and plus 1. Then our sigma x squared input noise power is nothing but 2 squared divided by 12, which is nothing but 1 by 3. So, we can equate it to signal to noise ratio, sigma x squared is equal to n times sigma x squared. This is sigma naught squared. So, then signal to noise ratio sigma x squared by sigma naught squared is equal to 2 to the power of 2 into b minus 1. So, what the note we are going to carry from here for FFT algorithm, a double length accumulator does not help us reduce round off noise, since the outputs of the butterfly computation must be stored in b bit registers at the output of each stage. That is what the note what we will be carrying from this. just like in FIR filter, by increasing the length of our accumulator, we could hold on to the result till the end of it, but here we will not be able to do it because we have to use it for the next stage. So, now we will see how the overflow is going to cause error. So, how we can avoid it? Overflow cannot be avoided. So, how you can by scaling and other things, how we can avoid the overflow errors? There are three methods. One is we can do a static scaling, that is dividing the input at first stage by n, that is a maximum this thing division what we are going to do it, or any stage by 2. So, that way we can incorporate the static scaling. The other method what we have is that is basically based on the dynamic scaling, that is dividing the input at any stage by 2 if the largest absolute input value is greater than or equal to less or equal to 0.5. Okay. So, then what happens? That is, we are taking the norm of magnitude of x of k, which is less than 1. So, 0 to less than or equal to k, which is less than or equal to n minus 1. So, how you will be taking the thing to find the norm? So, we will be equation is nothing but n is equal to 0 to n minus 1 x of into w k n. So, we have to take the norm of it, which is less than or equal to. So, we have assumed that twiddle factors have been scaled and then they are within the limit, then it becomes the magnitude of x of n. By scaling my input, then that is 0 less than or equal to k less than or equal to n minus 1, I can overflow error can be avoided, just like our FIR filters. So, if we have more than n minus 1 stages, the addition what we can take care of in our accumulator by having guard bits, and then later on we have to do the scaling. Okay. So, the first one, that is what we said is static scaling, that is dividing the input at any stage by n. So, what happens to the noise to signal ratio increases as n squared, or we call it as 1 bit per stage. That is, if n is doubled, corresponding to adding one additional stage to the FFT, that is what we just now saw it. Then to maintain the same signal to noise ratio, 1 bit must be added to our register length. So, this is our equation what we have it. So, we will be adding one more bit to that. So, we say our magnitude of x of n, we say that it is scaled by 1 by n. Then what happens to our sigma noise sigma x squared input, basically 2 by n whole square divided by 12, which is nothing but 1 by 3 n squared. So, we call it as this is our signal power, sigma x squared is approximately equivalent to n, and then signal to noise ratio will be our signal is sigma x squared by sigma naught squared, which is going to be 2 to the power of 2 into b minus 1 by n squared. So, what in this case the assumption of a white noise input signal is considered. In that case it becomes 2 by n whole square divided by 12 is our signal power. For a variety of other inputs, the noise to signal ratio is still proportional to what we call it as n squared, with only the constant of proportionality is going to change, as you can see the thing here. Okay. So, if we do dividing the input at any stage by 2, what is the thing is going to happen? So, I think there should be some trigger in your mind, because why we call it by 2 is we have a barrel shifter. So, we can shift the dividing is nothing but right shift by 1 bit is going to give us divide by 2. so that we need not have to spend any time in shifting our input. What happens? Very little noise, only a bit or two what we are going to get affected is present in the final array, and most of the noise has been shifted out of the binary word by the scalings. So, you will be seeing that sigma naught squared is approximately equivalent to 4 into sigma b squared, just we saw that because of the 4 butterfly, which is nothing but 4 by 3 into 2 to the power of minus 2 into b minus 1, and then we are assuming our magnitude or norm of x of n is less than 1 by n in this range. Then what happens to our input noise power? So, which becomes 2 square, assumption here also it is white noise signal what it is assumed, then it will be 2 squared by 12, and then this is 1 by 3 which is equivalent to sigma x squared is nothing but 1 by 3 n. So, the result of an increase of half a bit per stage holds for a broad class of signals with only the constant multiplier in this equation being dependent on the signal. So, what happens to our signal to noise ratio in the final? Sigma x squared by sigma naught squared, you will be seeing that 2 to the power of 2 into b minus 1 divided by 4 n in this case after substitution. So, the other one is we call it as dynamic scaling, that is we use the block floating point. So, what is it definition? You may be wondering what is the thing. What we say is the original array is normalized to the far left of the computer word with the restriction that our magnitude of x of n is less than 1, and the computation proceeds in a fixed point manner, except that after every addition there is an overflow test. Fine. If there is a overflow detected, the entire array can be divided by 2 and the computation is going to continue. So, the number of necessary divisions by 2 are counted to determine a scale factor for the entire final array. Then we will be calculating the signal to noise ratio, depends strongly on how many overflows occur and at what stage of the computation they occur. So, the positions and timing of overflows are determined by the signal being transformed. Thus, to analyze the signal to noise ratio in a block floating point implementation of the FFT, we would need to know the input signal. So, when we call the block floating point is because each stage we have different stages. So, we know each stage what is the input required. So, we will scale this input x of n, what we will call it the first stage, or I can call it as x1 of n, and then keep those values here. Do this in the fixed point mode operation. Then when we are coming out of it, either take these values and scale back. So, we will call it as y1 of n, which goes as input to the next stage, okay, which we call it as x2 of n. We can multiply and then do the rescaling of this, or in the end what we can do is if there is a overflow, then we will be dividing it by 2 in these cases. If it is not so, then we will keep these values till the end, and when I come out of here, whatever final I will put it stage, I will multiply with these values and bring it back into floating point value. So, that is one value where I know that just as an example. So, we have 0 0 1 1, okay, and the next one is 0 0 1 1 1, or the next value may be 0 1 1. So, I know that these two bits I can call it as left shift and then keep it as 0.11, and then I will be working, that is block floating point, I will calculate whichever the common, take it out and then use the rest of them to for my computation of FFT here, okay, stage 1 or whatever may be the thing. This is how our block floating point is going to work in our case. So, coming to the what are the real time FFT considerations we are going to have it. So, one of the thing is we have to consider the signal bandwidth, our sampling frequency, number of points FFT n what we want it, and what is the resolution. So, we have seen the DFT resolution. So, what we need it Fs by n, and maximum time to calculate our n point FFT. So, that is n by Fs what we are going to have it, whether we want to do fixed point versus floating point DSP. So, in the lab we have done floating point implementation. To do the fixed point implementation, we may have to consider the block floating point and then do it. So, whether we want the radix 2 FFT or radix 4 FFT. So, if it is power of 4 whatever input, it is advantageous to use radix 4, because it is going to be -1 or -j coefficients what we have to compute in radix 4. You can refer to the literatures to how to do the radix 4 implementation. So, we have seen the radix 2 here, but divide, that is even and odd parts what we have taken and then how we have computed. So, the next one is because most of the application is going to be, we will be using in the windowing filtering. So, what are the windowing requirements one has to consider. So, we saw an example in the lab, that is Kaiser window and then the rectangular window. So, how our output is going to get affected with the thing. So, now to put the thing, different radix implementation can be done. So, if it is power of 2, all of them what is taken is power of 2, some of them are power of 4, some of them are power of 8, what you will be seeing it. So, if it does not fit into any of this category and you are taking some radix format, how we can do the split radix format also. One can be 8 and then if it is order is 2 power 12, if we take the thing, I can have radix 8 1 and radix 4 what I can combine and then how I can do the split radix. So, that is what is shown in this table. So, as an example, this is the least n is equal to 16 what is considered, and radix 2 needs real multiplications of 24, whereas as you can see it has come down to 20 because this is power of 4, number of multiplications, real multiplications has come down to 20. In the split radix it needs also 20 in the case, whereas real additions in case of radix 2 we need 152 additions, in radix 4 it is 148 and split radix is 148. Just we will see the last one 1024, rest of it you can look at yourself. So, what we radix 2, as you can see that it needs 10248 real multiplications and 7856 in the case of radix 4. So, you will be seeing that how much difference you are going to have with radix 4 with radix 2, and then we cannot implement this in radix 8. So, that is why nothing has been given, and in the split radix still you can come down to 7172. Okay. And then same thing with respect to your real additions, it takes 30728, whereas radix 4 takes 28336, and then split radix is still lesser. So, depending on your application which radix format what you want to have it, that is the application may need 1024 or 2048 or 4096, or if you want to implement much more than that, you can see which radix format or different radix format at each stage what you can have it, and then combine and then take the output if it is not power of 2 also. Okay. So, we will see that how the our butterfly structure is represented in a flow graph, that is radix to 8 point decimation in time what algorithm what it has been taken. So, you will be seeing each point what we have it. So, you will be seeing that here you are seeing the 4 butterflies here, and in the next stage also 4 butterflies, and then in the last stage also what you have the butterfly, and multiplication and other things are represented with your weight factors as it is shown. And then we said that to contribute for any of the 1 input we need n minus 1 butterflies. So, there we have drawn everything. With the flow graphs it is easy to see that we need n minus 1 butterflies. Okay. So, we saw just now the signal to noise ratio. So, you can go through the thing. We have number of bits is equal to b bits, and then we have seen that noise generated by a butterfly at one stage is fed into the subsequent stages, that is in this case n minus 1 stages what we call it. So, then we said that our noise is represented in this way, that is n minus 1 into sigma b squared, and now you will be realizing for large n we can represent it as n into sigma b squared, which assumed it in the previous case. And then we have signal to noise ratio in this case is approximately given by this equation, that is 2 by n to the power of 2 b minus 1. So, if I want to this thing signal to noise ratio, we call it as proportional or inversely proportional to n and directly proportional to number of bits. As you can see that n is in the denominator and b is in the numerator. So, that is how by increasing 1 bit you can nullify on whatever signal to noise ratio what you want to get it. So, we said that overflow errors and scaling in FFT what it has to be done, maximum what we call it as that is you will be making it a dash is equal to 1 and b dash is equal to 1. In that case it will be less than or equal to 2 times max of a and then b. So, this implies that the maximum modules of the butterfly output increase from stage to stage by a factor of 2. So, if the inputs of butterfly of each scaled by 0.5, the output should not overflow provided the magnitude of the input data is within the permissible word length what we call it. So, as in this thing scaling, how we have considered 0.5 as the scaling factor and then deriving what will be the magnitude of it is illustrated by this example. So, we consider a dash is equal to our real part and then br into cos x plus bi into sin x, and this is our imaginary part, and then we assume a dash is equal to 2.4142 plus j, and then b dash is equal to minus 0.4142 plus j. So, how we have got this? If x is equal to 2 pi k by n, which is 45 degrees, then our cos 45 degree is equal to sin 45 degree, which is nothing but root 2 by 2. So, without scaling and with real and imaginary parts of inputs, each is set to 1. The limiting case we have from the equations from these above, what is it? A dash is nothing but 1.2071 plus 0.5 g, and then b dash will be this value. If all of them are set to 1, this is what we will be getting at. So, we know that what will be our maximum output from these butterfly structures. So, to see that by adjusting how many bits are required to keep our signal to quantization noise ratio required, we will see that processor one problem in this case. So, what it says, a hardware FFT processor uses fixed point arithmetic in its butterfly computations. So, estimate the maximum word length required to perform a 1024 point FFT with an output signal to noise ratio of 40 dB. In this case, you are lucky to have just 40 dB. So, assume that the input to each butterfly is going to be scaled by 0.5, which is nothing but 1/2 throughout the FFT. So, then signal to noise ratio equal, because we are scaling by 2, it is going to be 1/2 n into 2 to the power of 2 into b minus 1. So, we have been given signal to noise ratio in dB as 40 dB, substitute this, put it as 10 log on the right hand side. So, you will be solving this, then I need b minus 1 is equal to 12.14 bits, which is nothing but 13 bits, approximate it to the next higher number. Then system word length for this is equal to b is equal to 14 bits. So, you can see if I want to have the CD quality, which is 91 dB. So, if you are this thing scaling is 0.5. So, you can see that how many bits are required, you can work it out and then come back with the answer. So, this we have seen that how the quantization is going to affect our number of bits, and then how many endpoints what we have to choose it. And in the next class we will be covering overlap add and overlap save techniques to compute long input signal, because as you are seeing in the present case, the length of the input is also restricted to n minus 1, whereas in our real time application input is coming continuously. So, how we can apply this FFT using overlap add and then save in the next class. Thank you.